Okay, folks, what we're here for talking about today is our second real-world problem-solving and thinking situation. As I mentioned last time, the aim of the exercise here is to just look at a simple everyday situation and think about how we might use that as a basis for working with our science and mathematics technology. Now, consider the following situation. On our morning walk, my wife Patricia and I, with our dog Cece, see the following things. About halfway around, we see this in a front yard. As you can see, those two letterboxes have a bit of an issue. We continue on, and we see this. As you can see, that letterbox there is pretty much straight up and down. There's a third one there which is straight up and down, but this second one here suffers the same problem as that one there, as the ones on the left. So there's something wrong with the letterboxes. If we go for a close-up view on this one on the right, what you see is that, and as you can see, it's taken around from the other side. So it's leaning substantially to the left there in that right photograph. So the thing is, if we compare those situations to the third letterbox, which is this one down here on the left there, from a close-up, that's what it looks like. Now, it's pretty well straight up and down. And that little doggy there, that's Cece, the one dog. So here's the problem we have in this real-world situation. The first two letterboxes are not vertical, and the future for them does not look good in terms of their continuing to be able to function as a letterbox, because obviously if what's happening to them continues, eventually they will fall down. Now, that's basically, I see that, and what occurs to me is this situation provides us with a context where we can think about a very simple thing, but in terms of the science it offers, maybe not so simple. So let's think of this in an inquiry-based way. What I might do is present that evidence to the students. If you've actually got something like this in the schoolyard where that same thing was happening, I'd take them out there and show them that as a way of illustrating in the real world what it is that I'm trying to show them with the pictures. And then I'd pose this as my question, perhaps. What is causing these letterboxes to have this problem? Is it the letterbox gremlin, or is there actually some reasonable explanation we can come up with to explain it? Another thing we might ask is, how might we fix it? Now, stop the video now and take the time to consider these two questions and how you would answer them at this point. So welcome back. I wonder what you've come up with. But let's continue on our journey of exploration and see what happens. Now, what I want you to do first of all, when you're doing this sort of thing, one of the things you need to consider and get right is the science and mathematics and technology that's actually involved in the situation that you need to account for to appropriately construct a situation that the students can learn successfully in. If you pitch it at the wrong level without the required underlying contextual knowledge, they simply won't get it. Now, that's one of the things I was trying to get across in the case of the towel, in the big ideas one, the initial problem solving. What I want to do with this now is to consider what the science and maths is that might be able to be addressed through this context. Now, first of all, what I want you to do is, without a formal way of explaining it, with actual equations or anything like that, or even scientific language, how would you give a qualitative, descriptive understanding of this context? Now, it doesn't take a rocket science to see what the problem is. As you can see in both of these images, the people who built the letterbox put a big heavy brick letterbox on a concrete slab and they didn't put it in the middle of the concrete slab. So that's the cause of the problem. But the thing is, we have to be able to explain that in terms of the underlying science. A student, even in probably grade 4 or 5, could look at this and give a reasonable explanation in very non-scientific words about what the cause of the problem is. They could also explain to you how to fix the problem. Mainly take the letterbox and stick it in the middle of the slab. However, when it comes to explaining this in terms of the science and mathematics involved, it's not so simple. Let's think about it in actual scientific concepts of the things that we need to know to be able to understand from a scientific perspective why this actually occurs. Now, what are the science and maths ideas involved here? There are some. Obviously, you've got the letterbox on the top sitting on the slab, and the letterbox is applying a force to the slab. So there's this underlying concept of force. You've also got the slab is an object which actually has an area, and you've got a letterbox sitting on the slab which also has an area. So you've got an area sitting on another area, and for whatever reason the bottom, the whole thing is starting to tilt. Right? So they have to have this idea of the force being applied across an area on this slab. That brings in the idea of pressure. If you just talk about the slab and ignore the letterbox and say, why is the slab rotating, you would talk about it in terms of a differential pressure being applied to the slab. There's more pressure being applied at the back of the slab to the front of the slab. So from a scientific perspective, you could also talk about the idea of a system, which I haven't got on the list. That is, you can think about the letterbox and the slab and the ground all together as one big system, or you can pull out a part of the system, which in this case is the slab, and talk about what forces and things and pressures are acting on the slab only and describe it in terms of that. So the letterbox, instead of being a letterbox as an object, is nearly now something which is providing the force or the pressure, the force to the slab which exerts the pressure on it. So there's another idea that we can get at, which is quite sophisticated when you think about it. We've got to be able to take a system and break it down into its parts and think about what's happening only to a part of it. Now, another thing you could even get to is the idea of torque. That is, that the slab itself is actually rotating, and torque is what happens to an object. It's the way we scientifically explain what causes things to rotate. That is, you have a point of rotation and the force is applied away from the force of the rotation point. So there's another scientific concept that could arise out of this. You could also think about centre of mass, because if you look at this situation, if we were to draw this, if you did this in 11 physics and you said, draw a diagram of it, a force diagram, what they will immediately do is they will represent the letterbox as a point. That is, we're taking an object which has 3 dimensions and mass distributed over 3 dimensions, but we're representing it as a force at a point at the centre of mass. So that's another thing you could use could get into potentially here. Now, if you talk about centre of mass, you could also get into pondering, well, where the hell is the centre of mass on that letterbox? And where should we put the force in the diagram to represent that big 3-dimensional object? So then you could get into density distribution within the object and the influence that has on the centre of mass. Talk about uniform density, meaning that centre of mass is in the geometrical centre of the object, all those sorts of things. Now, the thing is, if you wanted to adequately model what's happening with that letterbox in science, you would have to have a reasonable understanding, or you should have a reasonable understanding of all of these things, because all of them are a part of that explanation. So you can see that a very simple situation in the real world requires a substantial amount of science and mathematics knowledge to underpin what is actually going on before a person. Now, so a person can do a qualitative descriptive understanding of this quite easily and explain it quite well, even in very low grades. But once we try to explain this in mathematics and science, the water gets very deep very quickly. And there's a whole heap of different things, even all things we don't even think about, that the person needs to understand to be able to adequately explain it scientifically and mathematically. Now, one of the challenges that we often have is that we often ask people in science and maths to do things where we haven't adequately considered for ourselves what all the underlying knowledge and conceptual understanding is that is required before the thing can be adequately understood. So, when you're designing STEM situations to teach, one of the things you need to do is look at the real world situation like we have here and go through a process of, before you even think about how you're going to teach it, think about what is the maths and science and technology or whatever, engineering, that's involved in the situation, and just have it all down on paper so that you know that then you can, when it comes to teaching it, you can then look at all of that and go, how do I teach this to the students I want to pitch it at? Now, if you looked at this situation, you might ponder, how could I do this? Right? I've got this context. I'm going to use it as a basis for teaching. How might I do it? Take a few seconds to ponder that, and we'll come together and I'll give you what came to my mind. Just one way. Okay, welcome back. What I came up with was this. I'm not saying this is right, wrong, or indifferent. I'm just saying this is one way to do it, and there'd be any variety of ways to do it. But you could perhaps do it as a project. What you could require the students to do is you can show them this problem, and then what their project is to build a model in the laboratory, first of all, that demonstrates the problem with the letterboxes, that they can actually build something and show that they can take that situation and get it to happen for themselves in a short period of time with some sort of a model. And it wouldn't be hard to do, just have some sand, not highly packed, give them they could have a board and they can put a thing or some weights on it, and they could move the weights around and see what happens and see if the thing stays, and a spirit level, see if the thing stays level, you know. It wouldn't be that difficult to do. Another thing you could require in the project is that the model must be able to show how the problem would be solved. That is, they recreate the situation first and then demonstrate a change in that model, so that now we can demonstrate that they understand what's required, what's causing the problem and how that can be fixed. Now that could be done by students at virtually any level, even in low, grade 4 or 5 could do it without too much trouble, I would expect. Now we come to the hard part though. What we need to get to, a student can do that without any great understanding of the science and mathematics involved. So whenever we do a project, and I'll talk about this more in the next problem, we need to be able to make sure that there is the academic rigour associated with it. So we always have to explicitly require something to bring out the science and the mathematics. So in this case, what I would ask for is an appropriate justification with the actual scientific and mathematical evidence, and they would know what I meant by that. I would have explained that. And they must provide that to support the model. That's both the first two parts, so that they've got some sort of adequate scientific understanding of what is actually happening. Now, that's my big idea for the week. Thanks for listening, and we'll get back to me and ask any questions that you like. Talk again soon.